In this video, we're going to explore a concept known as bond polarity. Bond polarity plays a very large role in the properties of certain molecules and is tied in very closely with the molecular shape, which we have already discussed. In order to really understand bond polarity, we have to take a look back at electronegativity. Recall that electronegativity is a measure of the tendency of an atom to polarize a bond. In other words, it's a measure of how much a certain atom in a compound will pull the electrons towards it. And so something that is more polar, for instance, an atom such as oxygen compared to carbon, means that when oxygen is a bond with carbon, the electrons in that bond are going to spend more time near the oxygen atom than they do the carbon atom. We discuss electronegativity as being on a scale. If we have an electronegativity difference that is less than 0.5, we consider this to be what we call a non-polar bond. In other words, the electrons are held pretty much equally, and so the electrons in that bond will not spend more time near one atom or the other. They'll spend their time around both atoms equally. If we have differences in electronegativity between 0.5 and 1.7, we consider that to be what we call a polar covalent bond. In other words, it is still a covalent bond in that the electrons in that bond are shared between the two nuclei. However, they are not shared equally at that point. The electrons are spending more time near the more electronegative atom, such as our bond between hydrogen and chlorine in hydrochloric acid. Chlorine is substantially more electronegative than hydrogen, and thus the electrons spend more of their time near the chlorine atom. This causes the chlorine atom to develop what we call a partial negative charge, as represented by the lowercase letter delta with a negative sign. The hydrogen side of the molecule will also develop a partial positive charge. This is to say that these sides of the molecule are kinda sort of a little bit positive and kinda sort of a little bit negative. Once we get to larger and larger electronegativity differences, above 1.7, then our difference in electronegativity is so much that at that point we have an ionic bond, where the charge completely transfers. For instance, sodium would completely transfer its electron to chlorine, and the positive charge on the sodium ion and negative charge on the chloride ion would now form an ionic bond. We're going to talk today a lot about polar covalent. As mentioned earlier, a polar covalent bond means that the electrons are not shared equally in the covalent bond, because the electronegativity difference is enough between the two elements so that the electrons spend more of their time near one atom than the other. And we can see that represented here in what we call electron density maps. Here, we can see a difference in electronegativity of 0, because it's a hydrogen-hydrogen bond, and so the electronegativities are equal, and our electrons, represented by this cloud here, spend their time equally around this atom and this atom. And so there is not one spot in the molecule where the electrons tend to spend more of their time and build up a bit of a charge. However, in HF, we now have a difference in electronegativity of 1.8, forming what we would call a polar covalent bond. And so we can see here that the electrons are spending more and more of their time near the fluorine atom, building up a little bit of a negative charge in this region of the molecule because electrons are spending more of their time here. That makes this region of the molecule somewhat more electron poor, and thus it builds up a little bit of a positive charge. And again, if our electronegativity difference becomes too much, then the electron is simply fully transferred over to the more electronegative atom, creating a negatively charged ion and a positively charged ion. And so, as we said earlier, a difference in electronegativity of 0 indicates that the bond is what we would call purely covalent. There is a complete equal sharing of electrons. Differences from 0.1 to 0.3 indicates that the bond is what we would call nonpolar covalent. In other words, there's pretty much an equal sharing. The electrons might spend a little bit more of their time close to one atom compared to the other. However, there's not enough of a difference there to develop what we would call a polar covalent bond. In the case of a polar covalent bond with differences between 0.4 and 1.7, now the electrons are spending enough of their time closer to one atom to start to develop a bit of a charge. And again, 1.8 or above would then indicate an ionic bond. We have to then take the bonds that are in a molecule and start to look at the overall effect of all of the different polarities existing in the overall molecule to try to determine if the molecule itself is polar or not. When we're doing this, what we have to do is investigate each bond in a molecule to see if it is polar or not, and then we've got to take a look at the overall effect of all of those different polar bonds. We'll see what we mean coming up. Here we see the example of I2. And so our electronegativities are equal since we have just iodine. And so we have an electronegativity difference of 0. So our electrons are shared equally. And so we would say that the bond between the two iodines is nonpolar. And since this is the only bond that exists in this molecule, this tells us that the actual molecule itself must be nonpolar as well. There is not one region in the entire molecule where electrons are building up, creating a charge separation. And so we have a nonpolar molecule. Here we have the example of hydrofluoric acid. As we saw before, the difference in electronegativity between hydrogen and fluorine is drastic enough that we will develop a polar bond. We represent a polar bond by drawing what we call a bond dipole, in which we draw an arrow in the direction of the more electronegative atom, and we put a plus sign at the end of that arrow over the more positive end of the molecule. And so this shows us the direction of electronegativity. This is a simple molecule made up of just two atoms and thus one bond. And so we can see then that the only bond in this entire molecule is a polar bond, and thus the entire molecule must be polar as well. And so we have a polar molecule. There is one region in the whole entire molecule that is building up a little bit more of a negative charge. We also have degrees of polarity in our bonds. The difference in electronegativity between hydrogen and fluorine is greater than the difference of electronegativity between carbon and fluorine. Thus, a hydrogen-fluorine bond would be more polar than a carbon-fluorine bond. Likewise, the difference in electronegativity between oxygen and fluorine is even less, and so a carbon-fluorine bond would have a greater polarity than an oxygen-fluorine bond. And so when we're attempting to determine if an entire molecule is polar or not, we have to look at a couple of criteria. The first is that it must have polar bonds to begin with. If we have something such as O2, then our electronegativity is the exact same for both, and so our difference in electronegativity is 0. So we do not have polar bonds, and so the entire molecule must not be polar. Likewise, if we have methane, if we look up our electronegativity values, we see that our difference in electronegativity between carbon and hydrogen is only a difference of 0.4. That is not enough for us to consider it to be polar covalent, and thus there are no polar bonds in this molecule. And so methane is also entirely non-polar. If we do have polar bonds in a molecule, we must then also consider the VSEPR shape of that molecule to see if the polar bonds have a cumulative effect or if they might cancel each other out. And so let's take a look at the example of water. What we have shown is the VSEPR shape of water. Recall that our Lewis structure of water would look like this. And so we would have a tetrahedral electron domain geometry. However, out of those 4 electron domains, 2 of those are bonding and 2 of those are non-bonding, leading us to a bent molecular geometry. And that's what we have illustrated here, is showing the actual bent geometry of our water molecule. Our difference in electronegativity between oxygen and hydrogen is definitely enough for us to create a polar bond in the direction of our oxygen atom. And so we have 2 bond dipoles in this molecule. We then must investigate the overall effect of those. If we draw those out right here, if we look at the 2 separate dipoles, we can consider one going up to the right, the other going up and to the left. And so if we think about the overall effect of those, the left and right components of those will cancel each other out. However, they are both moving in the upwards direction, and thus the overall effect of those is going to be a dipole going straight up. And that is what we see here. A bond dipole going straight up through the whole entire molecule. And so this molecule would definitely be considered to be a polar molecule because it does have an overall dipole. And so in other words, the oxygen end of this molecule will become kind of, sort of, a little bit negative, and the hydrogen end of this whole molecule becomes kind of, sort of, a little bit positive. Let's look in the case of carbon dioxide. So here we have a molecular geometry that is linear. We do have an electronegativity difference between carbon and oxygen that is sufficient to create bond dipoles moving in the direction of our oxygen atoms. However, if we look at both of these dipoles, one heads straight to the right, the other straight out to the left, they are going to cancel each other out. And so there is not an overall dipole in the entire molecule. The whole thing is non-polar. Remember, what we're really looking at when we're looking to see if a molecule has a dipole is if there is a region in the whole entire thing that tends to build up a little bit more of a negative charge. Since we have oxygen pulling electrons equally in both directions, we do not have an area in this whole entire molecule that is building up negative charge due to electron movement. And so overall, the molecule is nonpolar. And so we see here just several different examples of different molecules with their different geometries, and if they would have a dipole moment or not. Take a moment and look at some of these, see if they make sense. If you need to, feel free to draw out the Lewis structures of these, and then consider the 3-dimensional geometry. Look for your bond dipoles, and think about what the overall effect of those dipoles will be. Don't worry so much about the actual numbers, but just look to see if it makes sense that something like water is going to have an overall dipole compared to a compound such as carbon tetrachloride. Here we just see several other examples of looking at molecules that contain a dipole, but looking to see if that those dipoles cancel each other out or not. Here in BF3, we have bond dipoles between boron and fluorine. However, this is a trigonal planar molecule, and so all of these atoms are in the same plane. which means that all of these different bond dipoles will cancel each other out, and so the molecule is nonpolar. And so we can see that here, that we have basically equal electron density around the whole entire outside of the molecule. As opposed to CCl2O, carbon here in the middle, 2 chlorines and an oxygen. Now we have a little bit of a pull between the carbon and the chlorines, but we have a much larger pull between the carbon and the oxygen, resulting in a net dipole that will move straight up through the molecule like this. And then in NH3, ammonia, our trigonal pyramidal molecule, now we have 3 different dipoles pulling from hydrogen towards nitrogen. However, the 3-dimensional shape of this is such that the left to right components will cancel out, but we still have an upward movement. And so we will have a bond dipole moving straight up through the whole entire thing, as illustrated here with an increased electron density towards the top of the molecule compared to underneath. Here are several tetrahedral arrangements with varying dipoles. Take a few moments and really look through this slide and make sure that these make sense to you. Take a look at the varying differences in electronegativity to see if there are various bond dipoles, but then think about the net effect of those bond dipoles and where that might drive an overall dipole of the molecule, or if in fact, as on the end with CH4 and on this end with CCl2, they actually cancel out for no overall dipole. Here we're going to begin to take a look at the effect of various shapes on the bond polarity. In this first slide, we're going to look at the difference between PCl5 and BrCl5. I realize that the drawing is actually BrF5. However, the shape and effect on polarity will be the same between those two molecules. First, looking at PCl5, our difference in electronegativity is certainly going to be enough to create bond dipoles between the phosphorus and each of the chlorine atoms. However, when we think of the 3-dimensional nature of this molecule, drawn here, we begin to see that each of these dipoles will cancel out. We have our 3 equatorial bonds, which will cancel each other out. Those are all going to be trigonal planar, and so will cancel out. And then our 2 axial bonds, which will also cancel out. And thus, all of these different bond dipoles will negate each other, and we will have a non-polar overall molecule. However, if we then take a look at the shape of BrCl5 or BrF5 as shown here, the 3-dimensional shape looks like this. And so our overall VSEPR shape of this molecule is going to be a square pyramidal molecular geometry. And we can see here that we have 4 polar bonds. However, these are all in the equatorial position. They're all in the same plane and will cancel each other out. We do, though, have one remaining BrF bond that is not canceled out by any others. And so we would have an overall dipole in this molecule that is not canceled out, and thus this would now be a polar molecule. And so we start to see a difference in the polarity of a molecule based on the VSEPR shape of that molecule. Let's look at another example. Here we have SF4 versus ICl4 minus. In the SF4 molecule, we definitely have 4 different bond dipoles. However, when we now look at the overall three-dimensional shape of this molecule, we can see that our dipoles in the axial position of this seesaw-shaped molecule will cancel each other out. However, we also have bond dipoles in our equatorial positions. Drawn as we see it here, the so-called up and down portions of these will cancel each other out, but we still have an overall dipole that would move from left to right. And so we have an overall dipole in SF4, making SF4 a polar molecule. Let's compare that to ICl4-. Once again, we definitely have 4 bond dipoles in this molecule, but let's see what the overall effect of those is when we're looking at the actual molecular shape. Our molecular shape of this molecule turns out to be a square planar molecular shape. And so even though we do have those 4 dipoles, they are all in the same exact plane. These are all in our equatorial plane. And so that means they will all cancel each other out. And so we do not have an overall dipole in the whole molecule. And so the whole molecule is nonpolar. And so let's look at a couple more. Here we have ClF3 versus XeF2. In each case, we have a trigonal bipyramidal electron domain geometry. There are 5 electron pairs around our central atom. In the case of ClF3, however, when we draw out the actual VSEPR geometry of this molecule, we get a T-shaped molecule with bond dipoles that look like this. And so this dipole and this dipole will cancel each other out. However, we definitely have an overall dipole from our remaining one that was not canceled out. And so this entire molecule would be considered to be a polar molecule because it does have an overall dipole. XeF2, however, still a trigonal bipyramidal electron domain geometry with our 5 electron domains. However, the molecular geometry of this molecule is going to be linear. And so we can draw out our 2 bond dipoles, which we can see pretty quickly will cancel each other out. And so since there is no overall dipole in the molecule, the whole molecule is nonpolar. Take a few minutes and see if you can predict the polarities in the molecules of CCl4 and SF6 in order to predict if the entire molecule is polar or nonpolar. Start by looking at the overall VSEPR shape of the molecule, and then see how any bond dipoles will interact with each other to see if they cancel out or if there is an overall dipole in the molecule. If an overall dipole remains, then the molecule is considered polar. Stop the video now, try to figure these out, and restart the video to check your answer. Hopefully you were able to see in doing so that both of these molecules are nonpolar. There are definite bond dipoles between the carbon and all of the chlorine atoms, and there are definite bond dipoles between the sulfur and all of the fluorine atoms. However, in our tetrahedral shape of CCl4 and our octahedral shape of SF6, all of those bond dipoles will cancel out. So there is no overall dipole in the molecule, leaving the entire molecule to be nonpolar. One of the areas in which this is really important is looking at some of the properties of molecules. You might have heard the expression like dissolves like. What this refers to is that polar molecules will dissolve in other polar molecules, and nonpolar molecules will dissolve in other nonpolar molecules. For instance, oil and water. Oil typically is made up of different non-polar compounds, whereas water is absolutely a polar compound. Therefore, they won't mix with each other. If you try to mix together some water and olive oil, you'll see that you create two distinct layers in there. This is mainly due to the fact that water is polar and oil is not. Ethanol and water, however, are both absolutely polar molecules, and this is the basis of most of the bartending industry. For instance, gin, containing a lot of ethanol, and tonic water are both polar molecules, and so will mix together in order to make a yummy summer drink. So in this video, we've explored the effect that the Vesper shape will have on the polarity of molecules by looking at the overall effect of the differences in electronegativity and the shape of the molecule. If you do need some extra help in looking at these, be sure to come see me, or go to a past session or see a tutor.